Hello and welcome to another session of the Digital WE Days. My name is Silas Son and I will moderate this webinar today. The topic of the day is Stay Ahead of Time, Navigating Market Shifts and Miniaturization in Quartz and Oscillators. Our speaker today is Sarah Moschüz. Sarah, hi.
Hi.
Cool to have you here. She will hold the presentation and after will answer your questions. Sarah is product manager for EMC and SPI at Well Electronics. Quartz components are timeless, but are your designs ready for today's miniaturization and performance needs? So let's future-proof your circuits. Stage is yours, Sarah.
Thank you very much for the nice introduction and a warm welcome also from my side today. I would like to start directly and want to ask you, what have network switches, your smartwatch, access control, or your smart home, or even card payment terminals in common? All of them use frequency products. Often they're also referred to as the heartbeat. That's why you can see the heart in the slide. And frequency products are in the circuit to generate a precise timing for your application. By the broad range of applications that you can see on this slide, you can see that frequency products are really important nowadays in modern electronics. And that's why we need to make sure that your design is future-proof. So that's why we look today at the following points. We will look at what's the reason to redesign your circuit at the moment. What is the current market trends that will influence your redesign? And what parameters you need to consider when you redesign a crystal or even an oscillator circuit. And then to the end, we come to a small summary with what we just learned today. So what are reasons to redesign? Actually, most of the PCB designs nowadays are done like ages ago, even years or a decade ago. That means the market situation was totally different. So what you can find on a lot of PCBs nowadays is, on the one side, what you could call old package designs. This could be like THT parts with a metal can. This could be even plastic molded housing. Everything where you would nowadays say it's maybe not state of the art anymore for designing a crystal or an oscillator. At the same time, you see like non-standard sizes. What does this mean? You can get packages that are quite small, but not really as standard and common in the market. For example, a 6.0 by 3.5 millimeters is not so common anymore. Same goes with a pad layout. So for example, a two pad layout with a 3.2 by 2.5 crystal is not really common anymore. And at the same time, if you did your design like years ago, you might have used a big metal can part. And now you're faced with the problem that you want to make your design smaller, but the crystal is just quite big. So what's the real reasons that you're facing now? So on the one side, if you're using a non-standard package size, you will be faced with increasing prices and lead times. So you're maybe not faced directly with an end of life of your component, but you will be seeing that the lead times are increasing. So if you really need to make sure that your supply chain is safe, make sure to use a standard frequency product, because at the end, after a lot of years, you will see a lot of end of lives. So what you see in the market also with the competitors at the moment is that they make a lot of non-standard sizes end of life now. We try to avoid that, but you will definitely be faced with an increase in pricing and lead time. And like I said, on the other side, you will be faced with just the issue of making your frequency product smaller. So on the same side, what are the trends that we're currently seeing in the market that will be influencing your design? Like just mentioned, a lot of people and a lot of engineers are looking just for smaller crystals and oscillators. So if you would ask me nowadays, what is the standard size? I would say 3.2 by 2.5 millimeters is like the standard for crystals and oscillators. But we're already seeing a trend to going even smaller, and the new standard might be 2.0 by 1.6 millimeters. So make sure that you use a small crystal if you need, But also just make sure to use at least the market standard with 3.2 by 2.5 millimeters. So what's the next trend? Like I just mentioned, a lot of the old designs will be getting end of life. Maybe not this year, maybe not next year, but maybe in 5, 10, 15 years. And if you don't want to do the redesign in 5 years, you could start now already. So what do I mean with old designs? So like mentioned, it could be old THT metal can parts, it could be plastic housing. But if you look at oscillators, also 5-volt oscillators are already considered an old design. In this case, the problem basically is every oscillator is containing an IC, and 5-volt ICs are just not the market standard anymore. The market standard tends to 3.3 volt, 1.8 volt, but 5 volt is not what everyone is looking for at the moment. And then another trend that you will see is that you get just more accurate with your frequency product. Every frequency needs to be even more precise, even more stable to just match all the market demands for the end application. And last but not least, for oscillators, we also see the trend to move to variable supply voltage. So here you're more flexible, you have a wider range of voltages that you could use, just so you're more flexible in your design, basically. So what does this mean for the products that we're having at Worth Electronic? So our portfolio is split between normal crystals and standard oscillators. But for the beginning, we will look at the crystals. So what is a quartz crystal? Quartz crystal is basically just silicon dioxide with some silver electrodes in a package. So quite simple product. But for the crystal to operate, you need an oscillation circuit around it, but we will look at this in more details in a few slides. So which parameters are important if you do a redesign? So consider you have already an existing design with maybe an old crystal, maybe with a bigger crystal, and you want to shift to a more modern and smaller crystal. What do you need to look at? So you need to look at a few parameters: the frequency, tolerance and stability, the load capacitance, the trim sensitivity, and the ESR. But we will take a look at each of these values now in more details. So starting with the frequency. The frequency for a crystal is mainly defined by the thickness of the crystal blank inside the package. So it's a physical behavior, you cannot really change it. So you just stick to the limits that the crystal blank is offering to you. A rule of thumb here is the thicker the crystal blank is, the lower the frequency is. And this also shows the problems that you will be faced if you go to a smaller crystal. Smaller crystals usually means that also the height of the component is lower. Therefore, lower frequencies cannot be achieved in small-sized crystals. As a comparison, I have brought to you 3 different sizes that we offer at Worth Electronic. For the beginning, we have the HC494H SMX, which is, you could call, an old design. It's quite big. But here you can see the lowest frequency that we offer is 3.2768 megahertz. So already quite low. Then we have the CFPX 180, which is at the moment the standard size, 3.2 by 2.5 millimeters. Here you cannot get lower than 8 megahertz. So if you have a design that was previously 4 megahertz, you will not be able to use a smaller crystal because it's not possible to achieve. And if you go even smaller, like the one at the bottom, the IQXC26, the lowest frequency is 24. So you will be limited based on the package size with the frequencies you can achieve. Just to keep that in mind. Then we come to the tolerance and the stability. The tolerance defines the frequency deviation at room temperature, and the stability, the frequency deviation over the temperature range. Both of those values are not directly influenced by the size of the crystals, but as I mentioned with the market trends, everyone is tending to a more accurate frequency. So a lot of people try to improve the accuracy of their design when they redesign it. So here you just need to make sure what kind of tolerance and stability you want to achieve after your redesign. Then we come to the load capacitance, one of the most important values for a crystal. You can see here that we have the oscillation circuit of a crystal. Like I mentioned at the beginning, you need this circuit for the crystal to oscillate and generate frequency. This is the most standard circuit design. I would say 99% of the circuits are designed in that way at the moment. The part at the top is usually part of the microcontroller that is used together with the crystal. So you don't need to worry about that because that's integrated into the microcontroller. You just need to take care of the part at the bottom. So the crystal, 2 capacitors, and maybe a resistor. What does that mean now? In the datasheet, as you can see on the right, we usually specify a value for the load capacitance. Let's take 10 picofarads. For the circuit you're designing, that means that the whole capacitance that your crystal is seeing, which means the 2 capacitors at the bottom, as well as every stray capacitance you will see in your circuit, needs to match the value that you have in your datasheet. As you can see here, there is a formula to calculate it, which includes the 2 capacitors CA and CB. So you could say that's the easy part of the design. But at the same time, you can see in the formula that we have a stray capacitance. And here the problem starts, because the stray capacitance is everything based on your design. It could be the capacitance of your traces, could be input capacitance from your microcontroller. So you don't really have much influence on it, and you can also not measure it. So here you need to be careful when designing your crystal that you choose the right capacitors to match the datasheet values. The next value is the trim sensitivity. It's closely linked to the load capacitance and defines how much the frequency will change if you change the load capacitance by 1 picofarad in your circuit. So here you can see how sensitive is your frequency on changes in the load capacitance. And the trim sensitivity is really depending on the internal design of the crystal. So it will depend on the size of the blank, the shape of the electrodes, basically the load capacitance that you have in your circuit, and the frequency. Here's 2 small pictures of 2 different designs. So we have a 7x5 millimeter crystal, and we have a 3.2 by 2.5 crystal. And you might see that the electrode is slightly different in shape. The blank will definitely be a different size due to the different package size. That will mean you have different trim sensitivities for both of those parts. And to make it even more visible, we compared 3 part numbers. All of those parts have exactly the same frequency, and all of them have a load capacitance of 8 picofarad in the datasheet. That means for this graph, we imagine we have 8 picofarads in the circuit, so we have 0 ppm frequency change. But at the same time, you can see if you change the load capacitance, you will change the frequency. And depending on the size of the product, this change will be higher or lower. So maybe saying, okay, I did my design not correct. Maybe I have more stray capacitance in the circuit than expected, and my circuit has now 10 picofarad instead of the required 8 picofarads. What does that mean? That would mean that for the CFPX 180, we see a frequency change of minus 36 ppm. Taking into account that I said the trend is going to more accurate crystals, that means there is a high probability that this part is already out of the specification that you requested. Same might go with the others, but you can see the smaller the package size gets, the smaller the change will be. So the smallest size, the IQXC26, just has a change of minus 10 ppm, which might be still in spec, but it could be close to the edge already. Same goes into the other direction. You could end up with a circuit design where you accidentally have just 6 picofarads in your circuit. And here you can see the changes are even bigger. So the bigger size crystal has a change of 56 ppm. I can guarantee you that's out of spec of most of our crystals already. So most of our crystals are more accurate than that, and you would make sure that your part is out of spec here just by having the wrong load capacitance. So you can see this is really important, and it's also important to have in mind when you redesign your circuit. Then last but not least, for a crystal, we have the ESR. The ESR is also defined in the datasheet and is just describing the maximum resistance of a crystal. And this value is really important to consider when you design your circuit, which we will see in a few slides. And the problem here is if you redesign your circuit and have a smaller crystal in place than before, you will be faced with the problem that the smaller the package size gets, the higher the ESR will be. So you can nicely see in this graph that you will get a lower ESR if you have used a bigger sized package in the past. So the ESR will be increased if you go smaller in size, and this can cause a lot of problems in your design. That's why we're coming to the point of why is all of this important? Why have I told you about those values, and what does that mean for your circuit design? If you design a circuit for a crystal, you always need to think about the negative resistance or the gain. So the gain in your oscillation circuit, which is shown on the right side again, the gain of this circuit needs to be higher than the resistance of the crystal. Only if you can achieve that, the crystal will oscillate. You can see also there is a nice formula where you can try to calculate your negative resistance in your circuit. Problem here is that the transconductance of the microcontroller, this information you need to get from your IC house. Some IC houses show that in their datasheet, then it's easy and you can use the formula to calculate it, but most of them don't show that. But I think this formula is quite nice to show to you what you can do if you have a problem with your gain. What you can do is if you want to increase your negative resistance to make sure that the gain is high enough in your circuit, one thing is you can increase the transconductance of the microcontroller, but that might mean you need to search for a different microcontroller because that's out of your hand to just increase that. Or, second part, you could try to just reduce the capacitive load in your circuit. So you can try to reduce CA and CB, and if they have a smaller value, you will automatically increase the gain. So now I said the formula is not so easy to use because you need a lot of values. On the other side, you could also just test it. So what you can do is you can add a resistor in your circuit next to the crystal in series, and you can try to increase this value as long as the crystal is still oscillating. So the moment the oscillator stops to oscillate, that's the resistance value maximum that you need to use in that formula. So you try to find out how much resistance you can add in your circuit until the crystal is stopping. And what does that mean now, or why does this information is important? With this, you can calculate the safety factor. The safety factor is the ratio of the negative resistance or the gain in your circuit and the ESR of the crystal. And we usually tend to say if the negative resistance is 3 times bigger than the ESR, you can call it a stable oscillation. So the crystal will oscillate, it will work fine. You usually won't face any issues. If the safety factor is even higher, so bigger than 5 maybe, we would say it's stable in any kind of conditions. So it's stable over temperature, over all kind of variations within the batch. So you should make sure that it's at least 3. 5 is better, but everything below 3 will cause you a problem because you will always be at risk that if anything changes in your setup, and that could be temperature, that could be just a variation in the batch, could end up in an application that is not working because the crystal is not working. So you need to make sure that the negative resistance in your circuit is high enough. And then we have another value that is a little bit interconnected to that, and that's the drive level of the crystal. The drive level is again specified in your datasheet, and it gives the information what's the maximum power you can put onto the crystal without damaging it. So if you exceed the value of the datasheet, you're at risk of damaging your crystal. But at the same time, if it's too low, the crystal might not start to oscillate. So here you need to be careful. The drive level is mainly influenced by your circuit design, so by the IC you used, but also by the ESR of the crystal and additional resistors if you use them. So here you need to be careful. I would say all modern design crystals, so everything that is a metal or ceramic-based part with a metal lid, usually has the same drive level. So here you won't get a problem if you reduce the size. But if you have used one of the old metal can parts, they usually have a way higher drive level specified in the datasheet. So if you now switch to a smaller one, just be careful that you not over exceed the drive level specified in your datasheet. So as a small summary, if you design a smaller crystal, what is happening or what you need to consider? So first step is you decide you want to redesign. So you want to now use a smaller crystal than previously. You will be faced with the problem that the smaller crystal has a higher ESR. That's just something you cannot influence. This is something that is material-based, so you just need to take that into account. Next problem then is if you have a higher ESR, you will automatically have a lower safety factor. Just because you have increased the ESR, that means the ratio of negative resistance to ESR is lower. This could be still fine, so if you had a safety factor beforehand of 10, you might end up with 5 now. But you could run into a situation where the safety factor is now below 3. So that means you might not be able to guarantee a stable oscillation about all kinds of variations. So what do you do then? So usually the next step is, if you don't want to change your IC, what you could, but usually the first step people take is they reduce the load capacitance in the circuit. So they decide, if I need a higher gain, I reduce the load capacitance, which is a valid point and will work. And that will mean you increase the negative resistance again. That's good. Therefore, you have a better safety factor and you have a stable oscillation again. So just by changing the load capacitance, you might solve the issue with a higher ESR. But I would say there's a big but. Because as we have seen beforehand, when we compare different sizes with load capacitance and what happens if you change the load capacitance in your circuit, you might have seen the more you reduce the load capacitance in the circuit, the more sensitive you get to any kind of changes. So where your frequency was quite stable before, if you have a load change of 1 picofarad in your circuit, and the frequency might just change by, let's say, 5 ppm, 10 ppm, you now end up in a situation where if you have the wrong load, your frequency changes by 50 ppm. So if you do that, just be careful that you really selected the right load capacitance in your circuit. If you need any more details on that, you will find another webinar from me from last year about that topic, where we get into more details on how to select the right load capacitance. So we spend a lot of time with crystals now, but as I mentioned before, we also have oscillators in our circuit or in our portfolio. So what does redesigning the circuit means for an oscillator? So first of all, an oscillator is a crystal combined with an IC inside. So all the oscillation circuit that we just talked about, where we said, oh, please be careful that you do the right design, all of this is included in the SPXO directly itself. So you don't have to do much. You just apply a supply voltage and you will receive a signal. So quite easy, and therefore maybe the better solution compared to a crystal. So if you do a redesign, I would say there's 2 main cases. Case 1 is you used the crystal beforehand and now say, yeah, it was fine, but I want to use an oscillator. Or you say, yeah, I used an oscillator before, but I just want to be future-proof, so I reduced the size. So we can look into both of those cases now separately. If you reduce or if you want to replace a crystal with an oscillator, and the reason for that could also be you used maybe 8 megahertz beforehand, you now want to go smaller with your crystal size and noticed, yeah, but 8 megahertz is not possible anymore just due to the physical behavior of the frequency, you might need to swap to an oscillator. So the advantages here is you don't need the oscillation circuit, you don't need to care about the drive level, safety factor. All of that you don't need to consider anymore. You're more flexible with the frequencies because for an oscillator, it's quite easy or way easier to achieve lower frequencies in smaller packages because basically you have the small IC within your component, and this IC can multiply the frequency of the crystal blank, or it can divide the frequency. So you're just more flexible and you have way more frequencies available with an oscillator. The only thing you might need to consider is that if you use an oscillator, you need to think about filters for your input line or your output line. So in this case, I can recommend to you a webinar from my colleague where she talked about all of the filters you could use and you need to consider for your design. And then if you just say, I just want to reduce the size of my existing oscillator because I want to be future-proof, even better, because usually that will not influence the available frequencies. Like I said, with an oscillator, you're more flexible anyway. And also you will not significantly influence the current draw, for example, which is one of the other big or important oscillator factors. So I would say if you just want to swap from one oscillator to another, you don't really have to take care about a lot of things. Just make sure you use the right size. So that means we're coming to the end and we're coming to the summary. What is the recommendations I can give to you now? What kind of parts should you use if you do a redesign and what you should not use? If it's my personal opinion nowadays, I would say, if possible, use a crystal or an oscillator that is 3.2 by 2.5 millimeters or smaller. We still have the bigger sized crystals. We also don't want to make them end of life. But like I mentioned, there is the risk of longer lead times and increased pricing. So if you want to have the part with best pricing and lead time, at least take the 3.2 by 2.5 or smaller part. Then for oscillators, my biggest recommendation is try to avoid 5-volt oscillators. We also still have them in the portfolio. It was quite common 10, 15 years ago, but like mentioned, 5-volt ICs are just not so common anymore. Therefore, pricing and lead time will be increasing here as well. Then I would say try to avoid non-standard sizes. So everything that is not standard is maybe not the right choice for you. I would say if you select crystals and oscillators from our portfolio, I can guarantee to you that we only looked at the standard sizes, so you should be good to go. But in case you have used one of the non-standard designs previously, I would recommend to you switch to a standard design. And last but not least, I would avoid plastic molded parts. That was something done in the past. It was an easy way to create SMT parts, but nowadays the standard is the ceramic-based parts. So I would swap to them because standard means better lead time, better pricing. And then last but not least, if you do a redesign of your circuit to use a smaller crystal and to use all the recommendations I just gave to you, please consider the frequency, because maybe your frequency is not available anymore in the smaller size. Take a look at your ESR and your gain. So make sure that your oscillation is stable and check that the drive level is fine. If you've done all of that, if you used all our recommendations, I can tell you your application is future-proof and you don't need to do a redesign within the next 10 years. Which means I'm at the end and I hope I could give you valid insights on what's happening with frequency products at the moment in the market. And if you have any kind of questions, feel free to write them in the chat.
Yeah, thank you, Sarah, for your interesting presentation. Now we'll come to your questions. Before we start with the live Q&A, short information for you. You can now download the handout from the presentation from Sarah, and okay, then I would say we can directly start with the first question. What must be taken into account when selecting capacitors for the oscillator circuit of a quartz crystal?
So yeah, like I mentioned before, it's a really valid question. It's an important one because it will influence your accuracy of the circuit and the frequency. So a first recommendation is use an NP0 capacitor, so they're stable over temperature. Otherwise, if you have a non-stable capacitor over temperature, you will see even more frequency changes over temperature. So make sure you use a temperature stable capacitor. And otherwise, I would say you're free to select the size. The size of the capacitor will not influence. It's more the temperature behavior and just the normal capacitive value.
I think you just correct now. How can the frequency of the circuit be measured properly in the lab? How can we decrease the influence of the probe capacitance?
Yeah, you mentioned a good point here. If you want to test your frequency in the lab and you want to use a probe, you will often be faced with the problem that the probe has a lot of capacitance, which will automatically influence your frequency. So first recommendation would be for sure use a probe with low capacitance, but even those probes have like 1 picofarad, 2 picofarads and will influence your frequency. Even better would be if you have a separated output that is buffered from the normal oscillation circuit, where you can just take your frequency and measure it. Some ICs provide this function, so they have an output where you can just measure your frequency and you won't influence your crystal with your capacitance. It's not so common, so in this case, I would recommend at least the low current, the low capacitance probe, and then to, check that you haven't influenced your frequency with even more capacitance from any other connections.
Okay, thank you. Then I see no more questions left in the chat. When you have any questions, please write into the chat, and then Sarah will answer it via email in the next day. So yeah, then I would say we are finished for today. Thank you, Sarah, for your interesting presentation, for the answers. Thank you for your attention. I will share the link to our Digital WE Days homepage. We have a lot of other sessions during this week. So please register now, and hopefully you see us on our next session. And have a nice day. Thank you for joining, and bye-bye.